Surface integrals. Here we discuss how to evaluate a surface integral by using a double integral. We can also calculate the surface integral for parametric surfaces. And then we thirdly look at how to investigate and determine whether or not a surface is orientable, which is a funny word to simply mean that if you're dealing with a surface, you only want to deal with that surface location or space, and you don't want the surface to change directions on you without your control. So if you're on the outer rim of the surface, you want to evaluate the surface integral or the so-called fluid flow there. And then if you are wanting to investigate the fluid flow, for example, within the surface or pointing inward from the surface, then you want to focus there because things change if you go from the orientation from outward to inward. The fluid flow obviously would change, and so the fluid flow would not be there primarily based on pressure, fluid pressure. It might not be based on the volume, but it could be based on the shifting or the changing drastically of the surface itself. Now, we do understand that the surfaces will not be constant, so there will be some change, but an abrupt change in the surface could cause the calculation of the fluid flow to be skewed way off. And so we can talk about the orientation of a surface and then again the flux or the fluid flow across a particular surface. We can use the strength of the surface integral to be able to calculate the flux. So we begin by looking at the surface integral and how it's defined. We want to calculate, excuse me, turn the volume down on my phone. Want to calculate the surface integral here. Surface S is given by z equal to little g of xy. The surface is said to exist above a region in the xy plane. Now, from there, we look at the function and how it's defined, where here this surface integral is being calculated by the summation of some function f times the change in the surface, where the change in the surface is basically a trumped up arc length formula. And so this change in the surface is the square root of 1 plus the partial of g with respect to x squared plus the partial of g with respect to y squared, then times the base area. So this double integral that we call the surface integral, this double integral of the function with respect to the change in the surface, is really the surface area times the function, the surface area from a previous section. Here, this is the limit as the partition shrinks, gets smaller and smaller, approaches 0, of the summation of f of x, y, z with respect to each I iteration times the change in the surface. How do you calculate the surface integral? Well, let S be a surface given by the equation z equal to g of xy. Let R be its projection onto the xy plane. So if g sub x, g sub y are continuous on the region in the xy plane, and if f is also continuous now on the surface, that is continuous there, the continuity strengthened by the limit at all points, then the surface integral of f over s is given here by the double integral of f of x, y, z ds over s is then can be examined by the double integral over r, where all the terms are now in terms of x and y. So f of x, y, z becomes g of x, y times here the change in the surface. So let's calculate using that to our advantage. And what I'm going to do is to use this idea of G. I want to define here that G is Z minus little g of xy. And so if that be the case, then the gradient of G is equal to negative G sub x xy I minus G sub y evaluated at xy j, and then here plus k. Take the gradient of this G. I want to show you something, that now the norm of the gradient of G is equal to the square root of, we can start here, this is just 1 squared plus this term squared plus the partial of G with respect to y evaluated at xy here, and this is squared. We're looking for the norm, correct? So if that's the case, then the surface integral over the surface of f of x y z ds is converted to the double integral over the region of f of x, y, z becomes g of x, y. This is g. And then this is times, if you think, this is the gradient, the norm of the gradient of g times the change in the area. So if that be the case, then for this problem, capital G is z minus x minus y from here. Here this implies that the gradient of G is equal to negative I minus j plus k. And then its norm is equal to the square root of the negative 1 to be squared plus the negative 1 squared for the j, and then plus 1 squared. And this just gives us the square root of 3. I want to show you here initially how important this norm of the gradient is, because we'll follow its path throughout this entire section. And so now the region, so here we gather the information for G, but for this given information, it tells us something this tells us something here about R, the region. So what is the region? We can use polar coordinates. This is a circle, so the radius, it's from 0 to 1, and then theta goes from 0 to 2 pi. So this surface integral is the double integral here of over the region. Now the function f have to have f there is x squared plus y squared, but z squared becomes x plus y to be squared because everything is converted here to x and y. So this is x squared plus y squared, and then this is plus z, which is x plus y to be squared dA. So now we simplify this, and so this gives us the double integral over the region. Here this is x squared plus y squared plus x squared plus y squared plus 2xy. I better put that square root of 3 there for this term that's necessary, because this is a part of ds. Remember here that ds is equal to the norm of the gradient of g times dA. So I need that square root of 3. The square root of 3. This is dA. So let's simplify it further. This is the square root of 3, the double integral over the region. Here we get 2x squared plus 2y squared plus 2xy dA. So this is the square root of 3. I think we can go ahead and safely convert to polar coordinates or cylindrical coordinates. The integral from 0 to 1, looking at r, and then theta goes from 0 to 2 pi. This x squared plus 2x squared plus y squared is 2r squared plus this 2 times x. X is r cosine theta, and then the y is r sine theta. This is all times r dr d theta. And so let's continue simplifying. We have the square root of 3, the integral from 0 to 2 pi, the integral from 0 to 1. This is 2, I'm going to distribute this r through the parentheses, 2r to the third plus 2r, r, so r there and r here, r to the third cosine theta sine theta dr d theta. Integrate with respect to r. So we have 2r to the fourth over 4 plus 2r to the 4 over 4 times cosine theta sine theta. R is evaluated from 0 to 1 d theta. So letting r equal to 1, we have, this is the square root of 3 times the integral from 0 to 2 pi, and this just gives us 1/2 here plus 1/2 times cosine theta sine theta. Then evaluating r at 0, everything cancels out, so this is d theta. So now we evaluate the integral, or we integrate according to theta, or with respect to d theta. So this is the square root of 3. This becomes 1/2 theta. Here we use a u du substitution. Let u equal to sine theta, du picks up the cosine. So here we get, this is plus 1/2. I'm doing the evaluation, so we're going to integrate. So this is u. So I integrate u. I get u squared divided by 2. So the u is the sine. So we get sine squared theta all over 2. Theta is evaluated from 0 to 2 pi. So if you let u equal to sine theta du picks up cosine theta d theta, then all you have is just 1/2 u d theta. That 1/2 there. Well, 1/2 u du. So we get 1/2 times this 1/2 from here gives us 1/4 u squared. So that's just 1/4 sine squared theta evaluated from 0 to 2 pi. So here we have the square root of 3, and we get 1/2 times theta. This is plus sine squared theta over 4. Now let's do our evaluation. So we have the square root of 3. We evaluate theta at 2 pi. So this is 1/2 times 2 pi plus sine evaluated at 2 pi is 0. And so this is 0. And then we evaluate at 0, we get 0. So all we have here left is pi times the square root of 3. Now let's see if there's another problem similar. There is. So let's look at this one. Same argument. So we'll use here, this is the double integral over the region. That's where we're going. F of x, y, g of x, y. This is times now the gradient, the norm of the gradient of g times dA. So let's find g. So g is z minus the square root of x squared plus y squared. And I'm going to go ahead and convert that to cylindrical coordinates right now. So this is z minus r. So the gradient of g with respect to the r and theta becomes here the partial, but right, there's the partial of g with respect to r so this is the partial of g with respect to r I plus the partial of g with respect to theta j plus the partial of here of g with respect to this little z, which is just 1. So here this gives us negative I, there's no theta, then the partial with respect of g with respect to z, it's just 1, and that's plus k. So this norm of the gradient of g is equal to the square root of 2, right? At negative 1 squared plus at 1 squared, that gives us the square root of 2. So If that's the case, then let's see what we have. The function f is the square root of x squared plus y squared. Then it says plus z squared, but z is this. So if I square z, it gives me x squared plus y squared. And that gives us 2 times x squared plus y squared, which is the square root of 2 times r squared. And that gives us r times the square root of 2. So we'll use that for the function. So here this surface integral over the surface of the function f of x, y, z times the change in the surface area. Here this is equal to the double integral over the region of the function f, right, which is here r times the square root of 2. And I better write. Let me go back and write those steps. This is the function f of x, here y, and then g or z, which is g of x, y, times the gradient of the norm of g times dA. So now let's put in there what we have. This is the double integral of the function f. You remember it came out to be r times the square root of 2. Now the norm of the gradient of g is the square root of 2. We're going to convert to polar coordinates. So that's on r dr d theta. Now, again, this determines for us g, but this part right here helps us get the region. So what's the region from there? Let's see, the region r goes from 0 to 2. And then theta goes from, it's the complete circle. Theta goes from 0 to 2 pi. So you come here, r goes from 0 to 2. Theta goes from 0 to 2 pi. Well, the square root of 2 times the square root of 2 is just a 2. This is the integral from 0 to 2 pi, the integral from 0 to 2. This is r squared dr d theta. So now we evaluate with respect to r. We get r to the third divided by 3. I'm just going to write that 1/3 here with this 2. So this is 2/3, the integral from 0 to 2 pi. This is r to the third. R goes from 0 to 2. Here d theta. So that gives us 2/3 times 2 to the third, the integral from 0 to 2 pi d theta. So we get 16/3 theta. Theta is evaluated from 0 to 2 pi. That just gives us 16/3 times 2 pi. So it gives us 32 pi all over 3. Stop there. We'll break this section up into 3 parts. One for the surface integral directly. Then the second part that we'll come back to is computing the surface integral with respect to parametric surfaces. And then thirdly, we will define and introduce and calculate the flux, the fluid flow using the surface integral.